We'll continue in today's lecture from where we stopped. We could not finish all the examples we had for Coulombs Law. So let's go through this example before we move on to the new topic. In this example, we have the three charges, as you can see here, minus 1 microcoulomb, 1 microcoulomb, and then minus Q1, where the distances are equal between this minus Q1 and this negative 1 microcoulomb and positive 1 microcoulomb. We need to identify the correct direction of the total force exerted on the minus Q1 charge. Which answer do you think is the correct answer for the total electric force exerted on the minus Q1? Is it A, B, C, D, or E? Try to approach this problem from understanding the magnitude of the force first, and then after you figure out the magnitude of the force, you can define the directions of those forces. Such a problem can be solved by inspection, just by noticing that the numerator for the electric force is the same, and also the denominator is the same. However, the direction will be different. So to help you, remember when we introduced the electric force, we said that this electric force is K times Q1, Q2 divided by R squared. So in this case, the magnitude is the same, because I am evaluating the force on this minus Q1. And in this case, the minus 1 microcoulomb magnitude would be the same as the positive 1 microcoulomb. And in this case, if I am to call this one Q1 and this one here, let me call this one Q3, 2, and the 3. So in this case, this one would be Q3. And this one would be Q1. For F3. And since they are opposite, then the force would be attractive. So this one is F3. Now for F2, as a magnitude would be K times Q1 or Q2 times Q1 divided by R squared. And since they are alike, then the force would be repulsive, pointing away, which means that F2 would be this. And in this case, if you calculate the total, you would find that the total force would be pointing to the left. So the answer to this question is D. Okay, so now let's move on to the next topic, which is the electric field. So we will be looking at electric fields from individual charges, and those charges will be treated as point charges. And also the visualization of this electric field through the field lines. Next lecture, we will be studying uniform electric fields, motion of charges in uniform electric fields, and electric potential energy. So what is the electric field? The electric field is the influence of a charge within its surrounding. So if you have a point charge, you will see that this point charge is going to influence its surrounding such that if you bring a second charge close to it, it will exert, this electric field will exert a force, an electric force on that charge. So if I am here for simplicity, since we're talking about the electric field, we're introducing electric field, I will assume that the charge, the point charge that will generate the electric field is a capital Q. So the electric field is given by this expression, which is the proportionality constant, K, times the magnitude of this capital Q divided by R squared, which basically has a unit of newtons per coulomb. So a single charge, a single point charge, is able to generate an electric field in its surroundings. We need to distinguish between two fields here. If this point charge is positive, then the electric field will be pointing outward, in all directions outwards. If this capital Q here, that's point charge that is generating the electric field, if it's negative, then the electric field will be pointing toward this negative charge. Now, that capital Q that I am studying the electric field that it is generating. Now, if I bring a little q, so here I'm distinguishing now between this capital Q and this little q. If I bring a second charge closer to this capital Q, then the electric field generated by this capital Q will exert a force on this little q, such that the relationship of that force is this little q times the electric field. So the capital Q is the one that is generating the electric field, and the small letter q is the second charge that I brought closer to the capital Q within the electric field that this capital Q is generating. So what's going to happen? There will be a force exerted on this small letter q due to the electric field generated by this capital Q. Now, you need to keep in mind that the direction of this force will follow the direction of the electric field, however, defined by or influenced by the small letter q type. So as you can see here, if this small letter q is a positive charge, then this positive scalar will only change the magnitude of the force. If this small letter q has a negative charge, then it will flip the direction of the electric force. So the direction of the electric force in the existence of an electric field is defined by the sign of this small letter q. So let's talk about this electric field due to the positive charge and the negative charge. This is a positive charge, and as you can see, the electric field is pointing in all directions. So you can look at it as the flame of a candle. you will see the electric field is pointing in. However, the difference here, this electric field is a vector field. The electric field is pointing outward if it's a positive charge in all directions. If it's a negative charge, then the electric field is pointing inward from all directions. So if we look at the electric field at different distances from this charge, for example, you can see that the electric field at this point is smaller in magnitude than the electric field at that point. Why? Because back to the expression of the electric field is proportional to the magnitude of the charge that is generating this field, which is the capital Q, and inverse proportional to the distance squared, which is the distance between the point of interest and the pointed charge. That's why the further you go, the smaller the magnitude of this electric field will be. Same thing for the negative charge. The only difference is the directions. But magnitude-wise, same. The further you are from the negative point charge, the smaller the magnitude of the electric field would be. The closer, the greater the magnitude becomes. And it's not linear because of the inverse proportionality with the distance squared. However, the charge is linear, as we will see later on. So let's do this example to understand the how to calculate the electric field more. What is the electric field at a distance 1.9 10 to the power minus 8 meter from an electron? So my capital Q here, the one that is generating the electric field, Q is an electron minus E, which is minus 1.602 10 to the power minus 19 Coulomb. And the distance here is R, where R is 1.9 10 to the power minus 8 meter. So since the capital Q here is negative, it's an electron, then it makes sense that the electric field will be pointing toward this capital Q, right? Because we said that the electric field would be pointing toward the negative charge. So in this case, this is my electric field. At point P. So this is point P. There is nothing in that point. One single charge can generate electric field in its surroundings. So the point P here is a point that has no charges in that point. So if you look at the distance here, just to give you an idea, if this distance here is R, then how are you expecting the electric field to be pointing in that point, from that point toward the Q? Same thing if you look at a point that is at a distance R from here. Again, the electric field will be pointing toward this capital Q. Magnitude-wise, they're all the same. So here, just to distinguish that those are different. I will say E1, E2, E3. However, E1 in magnitude equals to E2 in magnitude equals to E3 in magnitude. Why? Because they're all at the same distance, which basically this is going to take me to finding if I'm looking in this plane, then you can look here at a circle that has a radius r. The magnitude is the same everywhere on that circle. Let me extend this further. I can look now at the sphere, not only a circle. So this is in the plane of my screen here. It's a circle. In volume, it's a sphere. All the points on that sphere that have the same radius would have the same magnitude of electric field. The direction would be different. Direction is always pointing toward the negative charge. If it's a negative charge, if it's a positive charge, then we'll be pointing outward. So in order to calculate now the magnitude of this electric field, which is the same at all those points that I have mentioned, K times capital Q divided by R squared, E equals to 8.99 10 to the power 9 times 1.602 10 to the power minus 19. I'm taking it as a positive because this is the magnitude of Q, divided by 1.9 10 to the power minus 8 squared. And in this case, the electric field, the magnitude of the electric field is 4 times 10 to the power 6 newtons per coulomb. Remember this number. We will be using it in the coming slides as well. And also remember that R is 1.9 10 to the power minus 8 meter. We will also be using this number in the coming examples. Yes? R here is the distance between the point of interest and the point. Because I'm taking the magnitude. I'm calculating the magnitude of the electric field. So it doesn't matter negative or positive. The negative positive thing here will define to me how is that electric field going to point. But as a magnitude, the electric field here is the same. In other words, the magnitude of the electric field, if I have this one electron, is going to be 4.4 to the power 6 newtons per coulomb for one electron, because I took the magnitude. If I replace this one electron with one proton, an equivalent to a charge of one proton, then I would be getting also 4 times 10 to the power 6 newtons per coulomb, because the magnitude is not going to distinguish between positively charged particle or negatively charged particle with the same magnitude. Does this answer your question? Okay. So remember those numbers, we'll be using them in the coming slides as well. So for one electron at a distance of 1.9 10 to the power minus 8, I got a magnitude of 4 times 10 to the power 6 newtons per coulomb. Okay. Now, based on the result we've just achieved, what is the electric field at a distance of 1.9 to the power minus 8 meter from an ion that has an equivalent charge of 2 protons? Which one do you think is the correct answer? A, B, C, or D? So instead of one electron, now we have an ion that is positively charged with a charge of 2e at the same distance. What are you expecting the electric field to be at that point? Hmm? B, D, the last one. Do you agree? I agree with you. It is D. Why is it D? Because the charge in magnitude has been doubled and the distance stayed the same, which means that the electric field will also be twice the electric field of that one electron. Right? The charge is twice the charge of the electron in magnitude. Distance stayed the same, and this means that the magnitude of the electric field would be twice the first case, the electron case. Make sense? So we understood that twice the magnitude. But is it away from the ion or towards the ion? She answered it right. It is pointing away. Why is it away? Because the ion is positively charged. And I know electric field for positively charged particles will be pointing away from that particle. So D is the answer to this question. Now comes the fun part. If I have a positive charge, I understand how does the electric field behave for positive charge. So this red thing is my capital Q. That's the one that's generating the electric field. At least I am evaluating its field. And those two are my small letter Q's. You can see that here it's negative and here it's positive. So how is that going to affect my electric force? Well, based on this expression, this small letter Q is the one that determines the direction of the electric force if I know the direction of the electric field. What does this mean? This means if my capital Q is positive and the electric field is pointing outward, and my small letter q is positive, then the force exerted on this small letter q would be in the same direction as the field. Make sense? Positive scalar. If my small letter q is negative charge, then it's a negative scalar. Then the direction of the force would be in the opposite direction of the electric field. Does this make sense? Negative scalar. Okay, so let's draw those cases. We have 4 cases to look at. And I will draw those cases for you here. So I want to start with my capital Q to be positive. And then at a distance r, there is a point P. Because my capital Q is positive, then my electric field at that point would be pointing extend the line between the point of interest and the point of charge, and put the field on S such that it is pointing away. So do like this, extend that a bit, and then draw the electric field. So this is the electric field due to the capital Q because the capital Q is positive. Now, if I bring my small letter q and put it right here on P, and this small letter q is a positive charge, what are you expecting the force to be based on the expression F equals to QE? Small letter q is positive scalar, then the direction of the force is the same direction of the electric field. Make sense? So here is my force. I want to do this in green. Why? Because this small letter q was positive. Okay, so let's look at case number 2. Capital Q is positive. Distance R. Point P. Since the capital Q is positive, I'll extend this line, and then this is my electric field pointing away. Then I brought a charge, this small letter q, that is negative. Then what do you think the electric force would be pointing to? Opposite direction. So why? Because now this becomes minus a q. Then the force would be pointing this way. Okay. Now I'll do the second cases at the same time. But now this capital Q is negative. Negative. This is R. This is R. The same point, P, P. Now that's a negative Q. Then the electric field will be pointing toward this minus Q. Then I have the electric field pointing this way. For both. Then I brought now my small letter q and I put it here. One of them is positive and the second one is negative. Can you tell me what direction is the force for number 3? Is it with E or against E? Is it E with E or against E? For number 3, this one. Against. No, with. Because this this small letter q is positive. And based on F equals to QE, it's a positive scalar. It will be in the same direction of E. So F is going to be like this. What about the last one? Against. Right? So those are the 4 cases. Now I want you to pay attention to what I'm going to say now. What we have done today is we managed to understand and learn the electric field and calculate the electric force exerted by this electric field on that charge, the small letter q. But this does not contradict with Coulombs law that we have studied in last lecture. Why? Look, positive, positive. They're alike. Force, repulsive. Positive, negative, attractive. Negative, positive, attractive. Opposite. Negative, negative, alike, repulsive. But today we've looked at from different angles. We approached it from electric field, finding the electric field of one charge, and then studying the influence of this electric field on the second charge. Right? That's what we have done. But at the end, the same result. No difference than what we have studied in last lecture in terms of exploring how is the electric force is going to behave. Any questions so far? Okay. Now let's look at those two examples here. What is the electric force experienced by an electron if it's 1.9 10 to the power minus 8, so same distance. Remember R, the one that we talked about? It is the same distance, 1.9 10 to the power minus 8 meter from another electron. So if you recall, we've done the magnitude of electric field from one electron at the same distance, right? And we found out that the electric field magnitude from one electron at that distance was 4×10 to the power 6 newtons per coulomb. Was that right? We just did it a few slides ago. So here I have my capital Q as being an electron at that distance. So now I know that electric field is pointing this way. And the force, because it's an electron, so my small letter q is negative, would be pointing in the opposite direction. So if I want to calculate the magnitude of this force, it would be the magnitude of the Q times the magnitude of E, which is, I know the magnitude of 1.602 10 to the power minus 19 times 4 10 to the power 6, and the answer is 6.5 10 to the power minus 13 newtons, pointing away. So what did we do here? At that location where we had the small letter q, which was also an electron, we knew the electric field. We knew how much was the magnitude of the electric field. Then we right away multiplied this magnitude with the magnitude of the little charge of the small letter q that we wrote and put at that location. That's it. That's what we have done. Now, the second part of the question is, what is the electric force experienced by a proton if it's 1.9 10 to the power minus 8 meter from an ion that is positively charged with an equivalent charge of 2 protons? We also did calculate the magnitude by the electric field generated from that ion at the same distance. If you recall, it was 2 times, right? It was 8 10 to the power minus 10 to the power 6 newtons per coulomb. Remember when we said that the charge and magnitude is twice the charge of the electron in magnitude, and that's why the electric field, the magnitude of the electric field was also twice the magnitude of the electric field of the electron, because the distance is the same. So here, my capital Q is 2e, and the distance is the same, r. But now, here we put electron. So this is small letter q was minus e. Here we put proton, so my little small letter q was 1e. So the electric field anyway is pointing away because my capital Q is positive and my small letter q is also positive, and that's why the force would be in the same direction of the electric field. So now here, my F would be pointing in this direction. So now if I am to calculate this force, which is Q times E, then this 1.602 10 to the power minus 19 times 8, 6, and the answer is 1.3 10 to the power minus 12 newtons. Again, pointing away from Q. So the force in both cases are pointing away, right? Again, negative, alike charges, look at the force, repulsive. For the lower one, alike charges, both are positive, force is repulsive, right? So for both cases, I have alike charges, and that's why the force is pointing away. Now let's do this example. Before we do the example, I want to talk about this point. So be careful when you're dealing with the electric field and the electric force, although both are vectors. However, keep in mind that one single charge can generate an electric field, but a force requires at least two charges to exist. Otherwise, the force would be zero, right? So you need two charges to have a force, but one single charge can generate an electric field. Keep this in mind. So let's do this example. In this example, we need to calculate the total electric field at the point D due to two pointed charges, Q1 and the Q2. One of them is negative and the second one is a positive. With the distances are given, and the angle between the two segments connecting those charges to the point of interest is also given. The coordinates is given to me. X positive to the right, Y positive pointing up. So, how to solve this problem? Let me draw this. So I have a Q2. I have a Q1. I have D, the point that I want to calculate the electric field at. This is R1. This is R2. This is theta. So I have here Q1 as minus 1.21 microcoulomb, Q2 as positive 3.40 microcoulomb, R1 as 3.19, 10 to the power minus 6 meter, R2 is 6.83, 10 to the power minus 6 meter, theta is 30 degrees. So I will put my coordinates right on the point D. X, Y. So the first thing I need to do is to draw those forces. I have E1 due to Q1, and I have E2 due to Q2. I'll start with the Q1. Q1 is a negative charge, which means the electric field generated at the point D should be pointing toward the Q1. So in this case, this is E1. I have a Q2 as a positive charge, and that's why it will be pointing away. So I will extend this line, and I'll draw E2 this way. So now I need to calculate the magnitude of E1 and E2. So I have E1 magnitude equals to K times Q1 divided by R1 squared, or E1 magnitude as 8.99 10 to the power 9 times Q1 positive 1.21 10 to the power minus 6, because it's microcoulomb, divided by R1. And R1 is 3.19 10 to the power minus 6 squared. In this case, E1 magnitude is 1.07 10 to the power 15 newtons per coulomb. E2 magnitude 8.99 10 to the power 9 times the Q2 magnitude, which is 3.40 10 to the power minus 6. That's a microcoulomb, divided by R2 squared, which is 6.83 10 to the power minus 6 squared. And E2 magnitude is 6.55 10 to the power 14 newtons per coulomb. So this is E1 and E2 magnitudes. Now I need to find the total magnitude. How do I do that? Well, I have those two vectors that I need to find the summation of those two vectors. And we've seen before that when we have two vectors, then we can work on their components. So we need to find the components for, we need to find E1x, E1y, E2x, and E2y. And then find the net x and the net y. So looking at E1, I can see that E1 doesn't have a y component. E1 has only an x component. All E1 is on the x-axis. So here, E1 x equals to E1, which is 1.07 10 to the power 15 newtons per coulomb. E1 y 0, no y component for E1. What about E2 x? E2x indeed is pointing in the negative direction. So this is E2x. So it is minus E2 cosine theta. E2x is minus, right away, I know now when I'm going to substitute it later on, I know that E2x will be substituted as a negative. That's why I found it here as a negative, and I will add it to the E1x. So E2x here is minus E2 cosine theta, which is minus, I'll put the answer right away, 5.67 10 to the power 14 newtons per coulomb. What about E2y? Is also a negative, but sine theta. So E2y is minus E2 times sine theta. And this one is minus 3.28 10 to the power 14 newtons per coulomb. Now, if I am to find the net component, then I would go E net x as E1x plus E2x, which is 1.07 10 to the power 15 minus 5.67 10 to the power 14. And the answer is 5.03 10 to the power 14 newtons per coulomb. So the net x component is pointing in the positive direction, right? Okay, so E net x component. What about E net y component? I only have the y component of the y. The E1 of the, of the E2. E1 doesn't have a y component. So E2, E net y is indeed E2y, and this is minus 3.28 10 to the power 14 newtons per coulomb. Fine. So E net x is here. This component is E net X. And this one is E net Y. Then my total is this. So this one is E net. And this one is phi. Then if I want to find the E net, E net X squared plus E net Y squared. And then this one is 5.99 14 Newton per Coulomb. And then this phi is indeed tan inverse of E net Y divided by E net X, which is minus 33.2 degrees, or you can say 33.2 degrees below X axis. So I'll stop here.